For decades, the idea of a humanoid robot was trapped inside research labs. Machines like Honda's Asimo were impressive engineering exercises, but they were slow, tethered, and highly brittle. They were strictly built for controlled demonstrations, completely incapable of handling the unpredictable chaos of the real world. By 2024, that narrative collapsed. Agility and speed replaced stiffness. Right now, highly articulated machines are walking onto active automotive assembly lines, handling parts and keeping pace with the flow of industrial production. Models like Figure 01 and Tesla's Optimus are leading this charge. They feature embedded vision systems, highly dexterous hands, and custom polymers designed to move and operate safely right alongside human workers. We are looking at a commercial reality. The barrier between experimental robotics and everyday industrial labor is gone. The timing of this leap is driven by a stark economic reality. Global supply chains are facing a massive structural shortage of physical labor. Corporations are struggling to fill warehouse and manufacturing roles, forcing them to look past human applicants to keep operations running. The cognitive barrier broke with the shift to embodied AI. Instead of just generating text, neural networks are now connected directly to cameras and sensors. This allows a robot to look at a messy room, understand the 3D space, and plan a sequence of physical movements to complete a task. Mechanically, these AI brains are now paired with cheap, highly efficient linear actuators. Instead of heavy hydraulic systems, these actuators use an electric motor to rotate a screw, converting rotational energy into a linear push and pull force. They act exactly like synthetic muscles, providing high torque at a fraction of the historical cost. A desperate labor market collided with cheap mechanical parts and spatial AI. That combination finally made the general-purpose robot a viable product. Enterprise buyers do not care about the science fiction appeal of these machines. A humanoid robot is simply a capital expenditure. It lives or dies on return on investment. Consider the current math. This chart illustrates the baseline comparison. Employing a standard U.S. warehouse worker over 2 shifts costs roughly $80,000 a year in wages and benefits. Compare that to a machine. Factoring in purchase price, electricity, maintenance, and software, the annual cost of ownership for a humanoid robot plummets to $24,000. The financial equation is undeniable. Replacing manual labor with synthetic workers yields a massive, immediate economic advantage for major corporations. To deploy at this scale, engineers bypass the physical world entirely. Using a method called sim-to-real, developers train these robots in high-fidelity digital simulations. Time moves faster in the virtual space, allowing a neural network to fail and learn millions of times before those polished skills are downloaded into a physical machine. Because the software is perfectly replicable, the hardware scales exponentially. Industry projections suggest we will see millions of these units operating globally by the end of the decade. That scalability pushes them far beyond the warehouse. NASA's Valkyrie platform, weighing 300 pounds, has spent years testing in degraded and hostile environments. They are learning to manipulate heavy equipment and navigate treacherous terrain to lay the groundwork for lunar and Martian colonies. Whether on a factory floor or the surface of Mars, humanoid machines can operate without oxygen, without sleep, and without physical limits. Factories are highly structured environments. The true friction emerges when these machines cross the threshold into the unpredictable space of our own homes. Models like the 1X Neo are specifically engineered for domestic life. They are built with soft outer layers and compliant joints to safely fold laundry, clean kitchens, and provide physical assistance to the elderly. This chart highlights a deep psychological barrier known as the uncanny valley. As a machine looks and moves closer to a living human, but retains a slight mechanical stiffness, it triggers an intense evolutionary revulsion. We are hardwired to feel deeply uneasy around something that mimics life, but isn't quite alive. Beyond the psychology, there is a severe data risk. To navigate a living room, a humanoid must use an array of cameras and spatial sensors. They act as roaming surveillance nodes, constantly mapping the intimate, unscripted patterns of private family life. The exact capabilities that make a robot a perfect autonomous factory worker turn it into a massive privacy hazard the moment it walks into a bedroom. Lawmakers are already moving to contain the fallout.
The European Union's AI Act is preemptively classifying many of these domestic and caregiving robots as high-risk systems, forcing manufacturers to clear strict conformity assessments before they can be sold. However, laws alone cannot regulate human emotion. As we increasingly assign the physical care of our children and our elderly to synthetic companions, we risk fracturing the basic social contract. Machines are endlessly patient. They never get tired, and they never judge. If we grow accustomed to that kind of perfectly compliant emotional outsourcing, the difficult, messy friction of genuine human interaction may start to feel too exhausting to maintain. The engineering puzzle of the humanoid robot is largely solved. The machines are here. The real test is figuring out how to live alongside them without sacrificing the empathy that makes us human.